Alina? So last time we talked about the type of steels and cast iron. Where is this coming after finishing the I'm talking about the iron carbon phase diagram. I want just to have you, and this slide basically gives you an impression about, again, a review of what we did, what is pure iron, what are the steels, what are the cast irons as well. But in addition to that, I'm giving you also like which applications actually for low carbon steels, which applications are you, which applications are the low carbon steels used, for example. These are used in car body panels, in beams, in sheets, in tubes. These are all low carbon steels. Between medium carbon steels, between 0.25 to 0.6, they are used in shafts, in gears, in bolts. Specifically, these you are going to use in the machine design. Machine design 1, basically, you will be designing shafts, you will be designing bolts. I guess in the machine design 2, you will be dealing with gears and bearings, so you will be designing those. You need to know which material you would be using, and high carbon steels from 0.6 to 1.4% by weight carbon. These are used to make wires, springs, knife, chisels, which are basically tools, and the cast irons, which are basically used to make machine bodies, cylinder blocks, and the engine itself, and so on and so forth. So it is there for you to come back to it if you need it in the other courses, which for machine design or your senior project as well. In the same way, we talked about the development of the microstructure in the different systems that we have seen, the binary isomorphous and the binary eutectic. We also want to see how the development of the microstructure occurs in the iron carbon alloys. We are not concerned with that much, because we already dealt with that. That is the eutectic point, and we know what happens going from here to there, going from here to there, and so on and so forth. So we are more concerned in the iron carbon steel actually with this area here. Area, we are making it larger actually, and we are zooming in to see the area more or better. So the parts that we are concerned with the development of the microstructure are the eutectoid. If you remember, last time we dealt with the eutectoid, we said this is the eutectic, this is the eutectoid point, and that point is the peritectic. So we are much more concerned with the eutectoid transformation which occurs there, and before the eutectoid we have the hypoeutectoid, and after the eutectoid composition we refer to that as the hypereutectoid composition. So let's look first of all what happens when we cool down at the eutectoid composition. If we are above there, we will be in the gamma zone, and in the gamma zone we will have polycrystalline solid, and this polycrystalline solid basically has this gamma, which is the austenite phase, has an FCC crystal structure. As we cool down, we are in the gamma zone. Nothing is going to happen until we reach the eutectoid point, isotherm. That's the eutectoid isotherm, that temperature. Once we reach there, once we go just below the eutectoid isotherm, the material wants to change from the gamma phase to two phases, alpha and the cementite. Due to the same reasons that we have explained in the eutectic point, the material wants to change from a single phase, which has an FCC crystal structure, to two phases which both have different crystal structure. The alpha has a BCC crystal structure, and the cementite there has an orthorhombic crystal structure. Not only that, but also that they have both very different composition in terms of carbon. The alpha, if you draw a tie line there, you're going to intersect, you're going to hit the line of alpha there. That's the alpha zone. And of course, you will hit that, the tie line hits this line also, which is the composition, well, basically at the back here, I should say, which is 6.7% by weight carbon. So you can see the composition of the alpha is 0.022, and the composition of the cementite at the back there will be 6.7, which have a drastically different composition. So for the same reasons there, it's going to go to this lamellar configuration. Lamellar configuration, which has the alternating layers of alpha and the cementite, alpha and cementite, alpha and the cementite, in the same way that we have looked at in the previous lecture. Yes, this one. And for the same reasons here, we have the same microstructure which looks like this. That is the lamellar configuration there, but in this time, carbon phase diagram. And this phase basically was discovered much earlier than the previous non-ferrous alloys. This phase specifically is got this lamellar configuration in iron carbon system. It is referred to as perlite, as I'm mentioning here. It's called perlite, and this microstructure is referred to as an adjective. It's perlitic microstructure, which is the alternating layers of ferrite and the cementite, which we have in the material. So you have alternating layers of alpha and the iron carbide, ferrite, and the cementite phases there. You can see we can make this is when we are referring to the different categories of iron carbon. This is low carbon, this is medium carbon, this is high carbon, and from here there onwards we have the cast irons basically. This perlite name, this perlite can be increased with increasing the carbon content in it. Why is that? Actually, the ferrite phase has very low carbon solubility. You see, the maximum carbon solubility is at the eutectoid isotherm, which is also very, very slow, very, very small. It is 0.022, very, very small amount of carbon it can accommodate. So if you increase the carbon content in the material, where is it going to go? It's basically going to go in the cementite phase, the iron carbide. But this has very high composition of carbon, very high concentration of carbon. It has 6.7% by weight carbon, and it does not form except at that, because we already said that this is a compound basically, and it forms only at 6.7% carbon, not at any other composition. So the perlite phase, where does this name come from? Basically, the name comes from the mother of pearl. You know the mother of pearl, pearl اللؤلؤ يعني. Mother of pearl, اللؤلؤ. This is the mahar, the mother of pearl, where the pearl is born inside, let's say, born or made inside, let's say. So this has on the surface basically these lines, which looks like very, very much like the mother of pearls there, and that's why it's called perlite. If we want to increase, let me go back. We want to increase, as we said, we are going to see that in a minute. We increase the carbon content. If we want to increase the perlitic structure, we basically can increase the carbon content, which we will see in a minute, and cause an increase in the perlitic structure. Basically, as again, where does that go? It goes in the development of the cementite, basically. So far, the important phases in the carbon steels that we have dealt with in the phase diagrams were the ferrite phase. The ferrite phase is nearly pure iron, basically, because as we said, the solubility of carbon in it is very, very small. This has a BCC crystal structure. The austenite phase, which is this one. The austenite phase has an FCC crystal structure, which is very much dense in carbon because it can accommodate, the solubility is very high compared to the ferrite phase. It has 2.14% by weight carbon. It can have a maximum of that much. And the third important phase that we have seen so far is the perlite phase, and the perlite phase consists basically of two phases, which are the ferrite and the iron carbide, basically, which is the cementite. Perlite has mechanical properties between the soft ductile ferrite and the hard brittle cementite phase because it consists of these two. Ferrite is the softest phase of steel. Why do we say that? Because it can accommodate very, very little amount of carbon. And that carbon is what makes the steel much stronger. So since it has very little solubility of carbon, and as we say, it is near to pure iron, it is the softest phase of steel. So when we mix when we have an aggregate of ferrite plus cementite there, the cementite is very hard. Why? Because it has high concentration of carbon. It makes the phase perlite hard and stronger. It is a combination of these two phases that we have. As we said, carbon controls the amount of perlite. We can increase the carbon content and therefore increase the amount of the perlite in the material. This microstructure, as you see, is for the low carbon content, as you see. So we have perlitic structure, and the black ones are the perlite and the white ones are the ferrite phase, basically. As we increase to the medium carbon content, you could see the much more perlitic structure developed, the black ones, as you could see there. And as we increase higher to high carbon steel, you see most of the material, most of the microstructure you see there is the perlitic structure. We can produce 100% perlite phase if we are at 0.76% by weight carbon, which is the eutectoid isotherm. Now, so far we talked about the development of the microstructure and the eutectoid composition. Now we want development of the microstructure below the eutectoid composition. What happens if we are below the eutectoid composition? If we cool down there, what is going to happen? As we cool down, and this is referred to as the hypoeutectoid steel. So if we cool down from less than 0.76, which is basically from 0.022 up to 0.76, same way we did before, right? So if we are cooling down from there, in this range, anywhere, here, passing through this triangle, which we refer to as the intercritical region. This is an important region. Actually, most of the research in steel goes in this area. So as we cool down, nothing is going to happen until we had this line, the solubility line. Then in this triangle, we have, what phases do we have? We have the gamma and we have the alpha. So the alpha is going to develop in the microstructure. At the beginning here, we have all gamma. As we go down, once we reach there, the alpha is going to form. Where is the alpha going to form, basically? At the grain boundaries. The formation of the new phase normally occurs at the grain boundaries. Why does that happen? Because at the grain boundaries, the bonds are not complete. The atoms are more energetic. And the change and the diffusion at those parts will be much easier than the change in the other parts. So that's why it starts with the grain boundaries. And as we go further down, as dictated by the tie line, you can see that the amount of the ferrite isn't going to increase. If you just draw a tie line at any point, at any temperature there, draw a tie line, you will see that this segment will be increasing in size as we go down further and further. So the amount of ferrite is going to increase, more and more and more to a maximum just above the eutectoid isotherm. Just above the eutectoid isotherm will be the largest amount of the ferrite developing there. And then just below the eutectoid isotherm, you can see the ferrite is a phase which is already formed, and it is stable. It is stable below the eutectoid isotherm or the eutectoid temperature, 727 degrees centigrade. It is stable. It is there as well. But the austenite is not. The austenite phase, which is here, is not stable here. It's going to transform. What is it going to transform to? It's going to transform to the perlite phase, which is the alpha plus the cementite phase, which we have here. So if we are above the just above the eutectoid isotherm, you will have that microstructure. If you jump just below the eutectoid isotherm, what is going to happen? Guys, what is going to happen? That austenite is this austenite is going to transform into this lamellar configuration, which is the alpha plus cementite, which is basically this phase, which is the perlitic structure which we referred to in the previous slide. So that ferrite which we have here, it's called pro-eutectoid ferrite. Why? Because it formed above the eutectoid isotherm or temperature. It's called also the primary ferrite, so you can call that primary ferrite, alpha prime there, or pro-eutectoid ferrite. And the ferrite which formed from this transformation of gamma to this lamellar configuration, it is another ferrite which we are having there, which we also refer to as the eutectic microstructure. Eutectic ferrite and the eutectic cementite, which form below the eutectoid microstructure of the material. So basically, in the calculations that if we for example are given like just below the eutectoid isotherm or at a certain temperature, what are the proportions? We do the same thing as what we did in the previous binary eutectic. If you remember, we did here calculations and we said we calculate above and then we multiply these numbers by 50% of the amount that we had here in the beginning. We already went through that, and this is so if we want to calculate how much here we have, how much of the proportions of the microstructure do we have, we need to first of all calculate what we have above the eutectoid isotherm, which means in this microstructure. We need to calculate how much we have alpha prime and how much do we have gamma, because in this microstructure that ferrite actually stays as it is, and then the austenite is going to transfer there. So all this perlite is formed, which is the alpha plus cementite, is formed, this lamellar configuration is formed from the austenite which is there, which you can calculate above the eutectoid isotherm. So you do that calculation first of all, which is for the above the eutectoid isotherm. So what you say there, just above the eutectoid isotherm, you draw a tie line, and then you say what is the proportion of the alpha there. It is this S, the far segment S divided by S plus R. This is what we are doing, S over S plus R. This is the weight fraction of the alpha, and then you can of course find the weight fraction of gamma, which is 1 minus weight fraction of alpha times 100. Both of them you can multiply by 100 in order to get the percentage there. So when you do that, then you do the calculations just below or below the eutectoid isotherm. Now at this point, you draw another tie line which is going to intersect here, and then you will say the weight fraction of alpha is equal to the S, which is the long segment, the far segment here, divided by S plus R. Of course, S will be 6.7 minus the eutectoid, which is the 0.76, divided by 6.7 minus 0.022. That is the amount. And this is the calculation. So it is S, the S, that the weight fraction of alpha, it's equal to that S divided by the total segment, which is S plus R. S, as I said, it's 6.7 minus 0.77 or 76 if you want. No, we are here. Sorry, that is not the one. Which is there, the composition we are at, the C naught, wherever we are. And we could be here, okay, anywhere. So it's 6.7 minus C naught, yani the composition we are at, because we can be at any composition there. That is the S divided by 6.7 minus the composition we are at, and this one. So if we are just above the eutectoid isotherm, we can choose 0.022, which is 6.7 minus 0.002. Now this should be multiplied by the amount that you get from here. So if this is, let's say, 40%, if you multiply that by 100, if this is 40%, then you have to multiply this by 0.4. And also, of course, when you do this calculation, you need to multiply this by 0.4. If that calculation is for 40%. If it is 30%, you multiply that by 0.3. Because why? Because when we are getting this value, it's based on what we have here, but the transformation to the perlite phase is happening from the austenite only, and the austenite here is how much? If this is, sorry, now if this is 40%, so you multiply that by 40%. Okay, so the gamma is 40%, you multiply it there by 40 and by 40. Why? Because they are being produced from the 40% of the microstructure only. If the austenite there was 30%, you multiply by 0.3, as we see. Okay, so this is a repetition of what we did before. I'm not going to do calculations more here. And the microstructure that you would be getting by this transformation or this development of microstructure, which is the hypoeutectoid, and will look like that. Most of the microstructure is ferrite, basically, the white grains that you see. And you have the paralytic structure, which is the alpha plus the cementite phase, the paralytic structure also shown there. On the other hand, if we mirror actually to what we did before, if you are cooling above the eutectoid composition, the same happens. You just need to replace the alpha phase which you have here, because here we have the alpha plus the gamma in this zone. And instead of these two, we will have the gamma plus the cementite phase. So if you cool down from there, as you cool down, you have polycrystalline gamma. Once you reach below that line, the cementite is going to form. In this region, you have the gamma plus the cementite. Cementite is going to develop and become bigger and bigger and bigger as we go down there, dictated by the tie line. And as we said, for the ferrite phase, it starts developing at the grain boundaries. Why? Because it's easier, as we said. And then as we go further down, more amount of the cementite is going to develop in the microstructure to a maximum just above the eutectoid isotherm. And if you then come just below the eutectoid isotherm, the cementite is stable here, so it's not going to change, but it's not going to further increase in size, but the gamma there is going to transform into this lamellar configuration. Again, for the same reason, it needs to do that fast, and in order to do that fast, it needs to just push the carbons to the side actually to make these lamellar configuration or the alternating layers of alpha and beta. And we do the calculation in the same way as we said, and we need actually to look at the gamma weight percentage, and you multiply here by the percentage of gamma, actually weight percentage of gamma divided by 100. So you do normally that weight percentage of gamma divided by 100 to have the microstructure proportions. In here you have You have the the primary cementite, you have the secondary cementite and the secondary ferrite, which we have, or you can call them also pro-eutectoid cementite, and you have the eutectoid microstructure, which are the alpha and the cementite phase. Any question, please? Any question, please? Hello, guys, are you with me?
موجودين دكتور.
Okay, no questions?
Clear دكتور.
Okay, if this is clear, we have finished actually from chapter 9. We can, I will keep that, all right? We can go and start chapter 10 now to link what we have in here and there. In chapter 10, what are we going to look at? We are going to look at phase transformation and microstructure in the iron-carbon alloys. We are specifically going to look at iron-carbon alloys. We are not going to jump back and forth to different, because this is the most important phase diagram. So we are going to look at iron-carbon alloys only. So what are the issues that we are going to address here? What we are going to look at, very importantly, is that transforming one phase into another phase takes time. As a precondition for the phase diagram, we already said that we produce using the phase diagram, if we follow the conditions there, like that the equilibrium is continuously maintained from the beginning to the end of the heat treatment of the material, then the phase diagram can give us the predictions of what the microstructures will be. These microstructures which we talked about are called equilibrium microstructures, equilibrium configurations, and that's why we called it equilibrium phase diagram. But following the very slow cooling, and that slow cooling is lower than the diffusion process, as we said, is very costly, and it's impractical actually to follow that. Why? Because in industry they lose a lot of money. Imagine you have the process of making something. When it goes to the heat treatment, you have to go to the furnaces, then you have to do very slow cooling. It could take 24 hours or more, and this makes a lot of cost in the process itself will have a bottleneck, يعني تعطيل المويه. It will take time, so it will lower the process speed. Actually, the production will be less. That's number one. You will be using a lot of energy in the furnaces to do very slow cooling there. So the cost of energy as well, and the cost of manpower which you're having there, which makes it impractical actually and ridiculous. So industry have pushed long back into what are the other options. What can we do in order that we increase the speed of heat treatment so that we don't lose all that money, in order to make things cheaper and to be sellable also at cheaper prices as well. So this is what we are going to deal here. How does the rate of transformation depend on time and temperature? We want to look at that. We want to study how is it, basically how can we slow down the transformation. And slow down meaning that we will go for higher cooling rate. Let's say, for example, if we cool this, the heat treatment that we do in the cooling process, we do that faster. What microstructures are we going to get? And how do these microstructures look like? Are they something that we can use or not? We are going to find out here that not only that it's possible to produce these non-equilibrium phases, but some of these non-equilibrium phases, which we refer to as metastable phases, are much more attractive than equilibrium phases and can be used also in practical applications as well, because as we said, When you produce equilibrium phases, this means that this microstructure, this configuration is stable and it's not going to transform. But when we have non-equilibrium phases, why is it bad? Well, non-equilibrium phases are bad and we cannot use them actually in making our machine elements. Why? Because they change they will change in the microstructure. And if they change, this means their property now is something. After a while, their property will change, and that is not usable actually in the design of any machine element. We cannot do that. But the metastable phases we can indefinitely use. Why? Because although they are not stable configurations, but in order to change, they take a huge amount of time, and you need also, in addition to that, a raise in temperature as well. So these things that we are going to look at in this chapter. Let's look first of all at what phase transformation means. Phase transformation is alternation in the number or the character of the phases. So how many phases you have, how these phases are going to transform, are going to change from, for example, BCC crystal structure type to an FCC crystal structure. That's a change which you have. Phase transformation takes place going from a liquid to a solid. So you have molten metal to solid metal, you have liquid water to freezing water, whatever, and from one solid phase to another. And we have seen that in the phase diagram as well. We can go from the liquid at the eutectic point, for example, from liquid to two solids, for example, and you can go from one solid to two solids as well, as we have done in the iron carbide phase diagram, going from gamma austenite phase to, for example, alpha plus the cementite, two solid phases. In the present, in the development of the microstructure for any single two phases, as we have discussed in chapter 9, this is presented already to you. Transformations can lead to equilibrium phases dictated by the phase diagram, chapter 9. So this is what we are already talked about. You can produce stable configuration, equilibrium phases, equilibrium configurations, which are stable at room temperature. If you follow the phase diagram conditions, very slow cooling, or it could lead also to non-equilibrium or metastable phases because of what? Because of insufficient time given for the transformation. So this is what we said. Why did we call the phase diagram equilibrium phase diagram? Because we leave enough time for the transformation to complete. Now, if we don't leave enough time, insufficient time for the transformation to complete, we will produce non-equilibrium or metastable phases. What are the equilibrium? This is a system that is at equilibrium when its energy is at its lowest value. It will not need to transform to anything else. Its energy is the least. This is what we say. The phase diagram shows the stable configuration. So if you follow very slow cooling, you allow the atoms to diffuse and the transformation to complete, you will reach to the equilibrium phases. The configuration is at its lowest energy and it's not going to transform to something else. On the other hand, metastable phases, the process required to change a system to a more stable state by diffusion may be extremely low, so very slow. So in order to do that, it's very, very slow. Diffusion is very, very slow. So if you cool down faster, a non-equilibrium or metastable phase will persist, will develop in the material. This is just a diagram to distinguish between the stable, the unstable, and the metastable phases. I like to distinguish between the non-stable and the metastable phases because these are actually different, because these are usable, but these are not usable. The stable phases, for example, which we produced from the phase diagram, is like that. It's very stable. Even if you push it back and forth, you heat it a little here or there, it's not going to change its position. It has high stability. Metastable phases are like this. They are stable and they will stay as they are unless you push them with difficulty. You raise the temperature high, for example, then this is going to fall. The unstable phases are like that. If you just leave it like this, if you just leave it, it's going to fall. So you don't need to do anything to it to change. No, it is unstable. And basically in practice, to make machine elements, we cannot use non-equilibrium phases because they change. Imagine you make your shaft from a non-equilibrium phase. Now the properties are like this. After some, let's say 10 days or 1 month, the properties change. So the material could become weaker and it could fail. So you cannot do that. But metastable phases, on the other hand, it's usable. Why? Because it does not change. Even if there is a change and it is a non-equilibrium phase and it could go to lower energy, it's not at its lowest energy level, but it takes a long period of time in order to change. So that's why it's practically used actually, unless we need to be cautioned that, for example, we don't use metastable phases at high temperatures. High temperature applications, these metastable phases cannot be used, and that's why knowledge about material science is important for the engineer in the selection of material specifically. So you cannot be using metastable phases in your microstructure for high temperature applications. If you know about this, you wouldn't do that, and you wouldn't fall into this mistake. Now, since we want to talk about transformation, we need to study what we refer to as the kinetics of solid state transformation. Kinetic, what does this basically or simply means? It means that the kinetics, it means the time dependence of phase transformation rate. Yani how does the phase transformation depend on time, basically. It's a measure basically that we do. We normally measure the the kinetics is measured by the fraction of the reaction that has occurred or the fraction of the transformation that has completed with respect to time. All right, so let us start that. So the solid state reactions, transformation from one solid phase to another phase takes long time to complete. And this is what we know from the phase diagram. Why? Because the diffusion process is very slow. Now, in the transformation, we have two stages basically. The transformation or the phase transformation involves two stages. The first stage, which we refer to as the nucleation, which is the formation of very small particles or nuclei of the new phase, like in the transformation that we saw from austenite to austenite plus ferrite. So at the grain boundaries, these ferrite were forming. So this formation of the new phase, which happens by the diffusion, the movement of the atoms in the austenite are FCC. They need to change to a BCC crystal structure type. Their bonding will look different, and their arrangement in the lattice or in the space will look different. So they need to move, the atoms need to move to change the configuration which is there. So favorable locations for the formation of the nuclei, النواة are the grain boundaries. And we said why that? Because of the higher energy level, because of the less bonding between the atoms there, and that makes the atoms there more energetic, as we said. Once the nucleation has started, then these nuclei are going to grow. Nuclei increases in the size until the equilibrium fraction given by the lever rule is attained. So they will grow in size, grow bigger and bigger until they, if it is a polycrystalline material, they impinge against each other and they form polycrystalline material there. The time dependence, as we are said, this is the studying of what we said, the kinetics of solid state transformation. In studying that, normally we look at the fraction of reaction that has occurred, or the amount or the fraction of the transformation that occurred, as a function of time. And in doing that, we normally produce what we refer to as the S-shaped diagram. This is called as the S-shaped diagram. The S-shaped curve is obtained when the fraction of transformation material versus log of time is plotted at, of course, a fixed temperature. We need to fix the temperature because at different temperatures, of course, we have different, you need when you study something, you need to fix some variables. You cannot be studying with all the variables changing. And in studying that, we see that we look at the fraction of transformation which completed in the material versus time, and we look at the log of time because the transformation takes a lot of time, and that's why we study with log of time in order to reduce the curve, actually to bring it back. We look because of the low transformation rate, we look at log of time, and we fix the temperature. And this is what we are saying, at a fixed temperature. So in studying that, we produce this S-shaped diagram, which shows the different positions. This is the time it takes for the nucleation. So if we put the material in the heat treatment process, for example, and then we check how much nucleation has happened, this is the time it takes for the nucleation to start nucleating something. This is the time it takes for the nucleation, and this is the time which takes for the growth to complete. So the total transformation time is from here to there. And as you can see, it is studied with the fraction of transformation completion. So in the formation there, you just produce nucleation here and nuclei there, and then it increases in the size and becomes bigger until it is fully transformed there at that time. So this S-shaped diagram is produced by studying the kinetics of solid-state transformation. Of course, it's a simple curve. It is for a fixed time, but in order to produce this simple and single figure that you see, there is a lot of time and a lot of experiments and a lot of heat treatments that you need to do in order to reach to this simple S-shaped phase diagram. Because why? Because we need to heat treat, for example, and then when we are heat treating, to see how much time does it take in order for the nucleation to happen. Well, this is a trial and error now. You have to try once, another time, a third time, until you see the nucleation has started for any microstructure, for example. And every time you are looking at this, for example, in the steel, let's say you want to see this phase has developed small nuclei of it, you need to do the grinding, the polishing, the etching, and microstructure visualization to see the microstructure. So all that process, every time, every trial that you do, you need to do this very meticulous job of doing all this. So actually just to see what happens there. And then you go through the growth as well. You get how much produce, and how much growth is going, and the completion. You need the more points you have on the curve, the better. So this is very meticulous job to produce one single pair S-shaped diagram. So just I'm telling all this for you to have an idea of that. It's not a simple diagram that you can produce in one experiment, or one test. No, it's a long experimentation effort actually to produce this, and this is only for a fixed temperature, for one temperature basically. Next, we want to look at the microstructure and property change in the iron-carbon alloys. Let us apply the basic kinetic principle, which we have talked about, for the solid-state transformation of iron-carbon alloys. We will see that the metastable structure intermediate between initial and final equilibrium states can be formed, and sometimes these metastable structures are desirable. Not only desirable, but we will see that they are actually more attractive than the stable configurations that we have, the equilibrium phases. If we can use them, this means that they are they have much more strength and ductility as well. So if you can produce a material or a phase like that, of course, it will be very interesting. It will be cheaper in producing it. Transformation will be faster, and so energy that you will be, money that you will spend in industry, they spend much less money to produce them. They will be higher in strength. They will be also comparable to the activity of the equilibrium phases. So this means that this is a very big advantage when we look at the metastable phases. The main reason for the formation of metastable phases is that for the formation of equilibrium structure, extremely slow and unrealistic cooling rate is required. But this was a reason for going to metastable phases. But when the scientists went to the metastable phases, they found much more there. They found that these metastable phases actually produce or give properties, combination between ductility and strength, much better than the equilibrium phases that we have. We will be exploring the relationship between heat treatment in this chapter, the development of the microstructure, and their mechanical properties. The phases that we are going to be interested in, the perlite phase, the bainite phase, the spheroidite phase, and the martensite phase. These are the phases that we are going to look at. To start with, we are going to look at the perlite phase, which you already know. From the phase diagram that we have seen, we saw that the perlitic structure could be produced if you go at the eutectoid composition and lower the temperature very slowly. Obviously, you get the perlitic structure, which is the lamellar configuration of the ferrite phase and the cementite phase. And this is what we are mentioning here, and the equation for this transformation was produced in the previous chapter. But now we want to look at a little bit different issue. We want to look at how does the kinetic of transformation affect the formation of different microstructure now. Let us look a point. Let us study now the transformation, and this is when we go below 727 degrees centigrade, we refer to as undercooling. Okay, so this is the undercooling which is mentioned here. Now, if we are at the eutectoid composition, let's say at a temperature of this much, just above the eutectoid composition, and if we jump to a temperature of this much, let's say, this is one heat treatment that we want to do, one development from here to there. So let us say this is our delta T, or let's call it delta T1. Delta T1. And let's develop the microstructure again in another way, jumping faster, jumping from here instead up to there, here. So this we refer to as delta T2, the change in the temperature, right? The change in the temperature. We do the undercooling delta T1 or the undercooling delta T2. That's faster. This is going much slower rate of the transformation. Of course, we are studying the kinetic of transformation. That's why we are going faster in the how does it depend on time? How does this transformation depend on time, basically? If we do that, if we jump in the temperature, or we have a smaller delta T, which is delta T1. If we have high jump in the temperature here, the absolute temperature here itself is T, let's call it T2. The jump that you have here, delta T, is high because you have big jump in the temperature, but the absolute temperature here is low, is net. So this is why I want to the delta T1 is smaller, as you could see, it is small, but the absolute temperature itself, T1, is high. Why? T1 is higher than T2. We are comparing two things here: the absolute temperature we are at, and the jump in the temperature that we are having here, because each one of them affects something else actually in terms of nucleation and growth. When we do a small jump in the temperature, what this does basically is that you will have a decrease in the temperature, not much decrease, small decrease, let's say, and some spots actually nucleate. In some spots, the new phase are going to nucleate there. But if we have a large jump in the temperature here, makes much more spaces in the material with low temperature, which means that in the microstructure you will have much more actually nucleation spots. Why? Because you jumped in temperature fast and you are now having much more areas in this material which will nucleate, much more spots at low temperature which will nucleate the new solid. The nucleation here becomes high. This high jump in the temperature causes that you have high nucleation. The high jump in the temperature, when you jump fast, this makes the probability of the nucleation is much higher than when you have a small jump there. Small amount of nucleation sites will be there. That's number one. Now, if you accept that, then, but also at the small jump, actually, this is the nucleation that we are talking about. Now the growth. The small jump in the temperature here, although the nucleation is slow, but since you have high temperature, the growth is high. This means that although they nucleated here, small amount of nucleation number, the number of nucleations or nuclei are small, but the growth is high. Why the growth is high? Because you are at a higher temperature. The higher the temperature, actually, diffusion in general is very slow in solids. But also the diffusion process at higher temperature in the solid is faster than the diffusion than lower temperature. Why? Because at higher temperature, the atom will have higher energy. And that's why at higher, when you have a small delta T, you have higher temperature there. The T1 is large. The absolute temperature itself is large. And that's why the growth, actually, these are going to grow bigger and bigger and bigger, faster than the other case. These are going to grow faster. They are going to grow faster. The nucleation is slow, yes, but the growth is fast. Here in the other case, the nucleation was high, but since you have high delta T, you are at a smaller temperature. Delta T2, the absolute temperature there, is small. So that's why the growth is what? At low temperature, the growth is small. The growth is very slow. Why? Because at low temperature, the diffusion is much slower there. And that's why they grow slowly. They end up with having what? With having a microstructure, basically, which is very, very fine. Why? They grow very slow, and they allow even for more nucleations to happen in the material, as we have here. So we have much finer microstructure here than the other case. In this case, these are going to grow, but they are going to grow to a much coarser microstructure. Let's have, since we have 4 there, let's make it 4 or 5. So this will be much coarser microstructure than this microstructure because of these two different things. The delta T affects the nucleation. If the delta T is high, nucleation is high. The absolute temperature itself affects the growth, basically, of the nuclei. If the temperature is high, the growth is high. If the temperature is low, the growth is low. So these two things are affecting the microstructure of the material. This ends up, if we have a small jump in the temperature, we will end up with a coarse microstructure. We call this coarse microstructure. If we have a high jump in the temperature, this leads to a fine microstructure. You could see we can then therefore control the type of perilytic structure that we are having. We could produce a fine microstructure and a coarse microstructure. And of course, are they having the same mechanical properties? Obviously not. We will be talking about this next lecture. The growth of pearlite from the austenite, as we already mentioned, it happens by the transformation. From this to this, from the austenite to the pearlite, it needs to change the phase from one phase to two different phases, which have drastically different compositions. So the atoms of the carbon are pushed to the side there. They gather with high concentration of carbon there. They make the cementite phase here, and that is the very low carbon composition that you have, makes the ferrite phase. And as you can see there, here is what we are looking at. Reaction rate increases with the delta T, as we have seen here. So if you have, that is the pearlite, the fraction or the percentage of the pearlite produced, and that is the log of time, which you have here. This is the S shape for the different temperatures here. This is for 675, for 650, that is at 600 degrees centigrade. You can see when you jump from that temperature, let's say above the eutectic isotherm, to 600 degrees centigrade, which means that you have a large jump, and the delta T is large, and this is what we are saying. The delta T is large, the nucleation time is very slow. Transformation happens very fast, but then the growth becomes slow. And on the other hand, if you jump fast from, let's say, above the eutectoid isotherm, above 727 degrees centigrade to 675 degrees centigrade, above that. So so your delta T is smaller there. If the delta T is smaller, then the nucleation times becomes much larger. Nucleation takes time until it produces, but the growth is faster. But the slopes of these lines are not realistic because we are looking log of time here. In doing so, and these are the two effects that we have.
Victor?
Yes.
Time is up.
Okay, just give me 1 minute. The nucleation rate increases with delta T, as we have already mentioned, and the growth rate increases with the absolute temperature of the material. I am going to stop here. Next time we are going to continue from here. Any questions, guys? Any questions? Today is your test, right?
Right.
All right, let me put those aside, and I need to stop the recording so that we save it.